And we have liftoff of the Space Shuttle Columbia, continuing space research through satellite technology.
On February 25, 1996, NASA and Italian researchers made a bold attempt to harness the power in the atmosphere. They generated electricity with a satellite on a wire.
Good work. Let's make sure we stay that way. I understand.
The mission was part of a new experiment of tethering satellites in space.
The experiment was based on the simple principle that when you move a conductor through a magnetic field, electrons start to flow. This generates an electrical current that can flow through a circuit. The satellite was thrust into space using small gas jets, and a 13-mile-long cable began to unreel.
If you put a wire inside of that tether, you now have a moving wire that moves across a magnetic field. A magnetic field, in this case, is Earth's magnetic field, and the motion is the motion of the space shuttle moving.
How's dragging a 13-mile-long wire, how does that generate current?
Fast, high velocities, orbital speeds.
Yeah, the orbital speeds, 17,500 miles per hour. So you're just dragging a 13-mile-long wire, and it generates a tremendous amount of current. How does that work?
Lying down here, Jeff.
The moving wire in the Earth's magnetic field generated 3,500 volts. Enough energy
This wire does not have a loop.
to power a space station.
So the question is, how did NASA know that just dragging a 13-mile-long wire was going to generate enough electricity? All right, so we've been dealing with Faraday's law. Röhrstedt discovers that the current causes magnetism. Faraday discovers that by using magnets, you can also generate current. The only thing you have to do is change the strength of the magnetic field inside a loop, the current loop. Increase the strength of the magnetic field, the current goes one way. Reduce the strength of the magnetic field within the loop, the current goes the other way. So as this so happens, if you vary the strength of the magnetic field within the loop, it's going to generate current. That's it. This is known as the Faraday's law. Any variation of the strength of the magnetic field inside the loop is going to cause current. Because the current keeps changing direction, it's known as the alternating current. Direction of the current is alternating. Not only the direction, but also the value of the current is alternating. Eventually, it was discovered that it's the amount of magnetism, the change of the amount of magnetism intercepted by the loop is responsible for the current. So instead of moving the magnet back and forth, you can also change the area, the amount of area exposed to the magnetic field, which you can do by spinning that area inside a constant magnetic field. All right, so that becomes a Faraday's law. All right, so any variation within the strength of the magnetic field, or any variation of the strength of the magnetic field within the area of the loop is going to induce current. That's what it means. Or you can keep the magnetic field constant and then vary the size of the area exposed to the loop by spinning it. Either way, you're going to end up generating current. So these two concepts could be combined into a single concept. The concept of flux, what's happening is the magnetic field is flowing through the area of the loop. So this represents the amount of magnetic field intercepted by the loop itself. It's a dot product, so the angle is going to matter, the angle between the magnetic field relative to the area vector. All right, so the amount of magnetic field intercepted by the area vector is going to be cosine of that angle that you're looking at. So if you vary the strength of the magnetic field within the area, it's going to change the flux. It's going to generate current. If you change the size of the area exposed to the magnetic field, it's also going to change flux. In turn, you will be able to generate current. So the next question is, change of flux, does it induce current or does it induce voltage? The answer to that question is straightforward. Voltage is what drives current. So any variation of flux is going to generate current, but what happens in reality is it induces voltage, which is known as the electromotive force. And the voltage in turn is what generates the current. So change in flux induces voltage, and voltage is what drives current. Of course, there's a negative sign up front, and this negative sign comes out of the Lenz's law. It tells you about the direction of the current. Mathematics here is mathematics and physics always tell you if you know how to read math. The definition of the Lenz's law is encoded within the mathematics, which means that the electromotive force, which is that's the voltage, is going to point in the direction which is going to oppose the change in flux. The negative means it's going to oppose. All right, so electromotive force is going to point in a direction which is going to oppose any change in flux. That becomes the Lenz's law. All right, so Lenz, the guy, obviously he came up with the Lenz's law under his name. The purpose of the Lenz's law is to figure out the direction of the induced current. Lenz's law.
You're messed up.
Is it better?
Yeah.
All right, give yourself 5 points. All right, so according to the Lenz's law, the current is going to move in a direction. Induced current is going to move in a direction that's going to oppose any change of flux. So I'm changing flux by moving the magnet in forward direction. So in essence, what I'm doing is I'm increasing the strength of the magnetic field intercepted by the loop. So the induced current is going to move to cancel out that change. It's going to move in a direction that's going to cancel out that change. So induced current has to move in counterclockwise direction so that the induced magnetic field is going to be pointing in the opposite direction of that change. So it's going to be moving inward in essence. All right. Okay, this example is worth going over one more time. All right, so I'm just going to increase the strength of the magnetic field intercepted by this area. All of a sudden, out of nowhere, you got one magnetic field that's just sticking out of the page, and then I'm going to try to get a second one going. All right, so I'm going to get a second one. All right, so as soon as I increase the strength of the magnetic field from 0 to this, the current is going to move in such a direction that the induced magnetic field is going to try to cancel out this change. So the induced magnetic field has to be pointing into the page, right? For the magnetic field to point into the page, the current needs to move in the clockwise direction. All right, that's it. All right, so that's all the review that you need on that one. Okay, so current is going to move in a direction that's going to oppose any change in flux, basically. So that's how we figure out this direction. All right, so we've been generating current the same way for ever since 1880s. Just mechanically spin a coil inside a constant magnetic field. 60 times per second is the industry standard at this point. So mechanically spinning it could be running water, pressurized steam, wind power, or whatever. So this thing is going to be spinning 60 times per second. All right, so mathematically, all right, I'm not going to go through everything. I just want to go through a few things as a reminder. So in essence, you're changing the flux. Faster you spin this thing, the more this flux is going to change, the more the current is going to be, right? All right, okay, I'm going to just go to the next one, I think. Okay, because this is the one that we didn't do. We did the previous one. This will be a good review one. Okay, this is the other one was for college physics students. This is for university physics students. Now that you guys have an understanding of what's going on, let's just repeat the same thing using a little bit of math. It's not a big deal. All right, so change of flux is what generates the electromotive force, right? Electromotive force is your voltage. All right, so change of flux within a single loop is going to generate this amount of electromotive force, this amount of voltage. If you double the loop, you will end up doubling the electromotive force. If you have 10 loops, 10 turns, the electromotive force is going to have 10 times faster. That's what it means. All right. So you're changing the flux for each and every single turn. And as a result, you're generating this amount of electromotive force, this amount of voltage. Again, you got the negative sign because of the Lenz as well. Definition of flux is here. This is the dot product that you're looking at, expressed in terms of a scale product. All right. Theta here represents the angular displacement. This represents the angular velocity, which is the same as angular frequency. I don't care what the textbook says. And this is the time that you got. So angular displacement can be expressed in terms of angular velocity times time. All right, in essence, what you're doing is you're spinning this coil inside a constant magnetic field. So B is going to be constant. You're not changing the area. You're just changing the area which is exposed to the magnetic field. In essence, you're changing the angle. And you're changing the angle within a certain time period. So how fast you're changing the angle can be expressed in terms of your rotational velocity within that time period. So multiplied by T. So this theta becomes this expression. Yeah, do that, you know. Anyway, so that's it. So the only thing which is changing in time is this cosine of omega t. So the cosine of omega t is the same as sine of omega t when you take the derivative of it. All right, so the derivative is taken with respect to t. All right, so it's going to give you sine of omega t times omega. So you pull the omega up front, and there's a minus sign in front of it as well, because when you take the derivative of cosine of anything, it's going to give you a negative sign of anything that you got. All right, so this is the expression that you got. So just ignoring the mathematical BS, let's just focus on this formula. All right, so how you get to this point is trivial. Right? It's calculus. Now that we are here, let's just park here and then just discuss what this formula is saying. What this formula is saying is the strength of the voltage is going to change in time. It's going to go up in time. Not only the strength is going to change, also the direction of the voltage is going to keep changing. All right, at this rate, which is omega, which happens to be the frequency that you're looking at. All right, so that's what it means. And it's going to vary between a positive of this value that you're looking at, MBA omega, and the negative of that value. So MBA omega that you're looking at is the maximum voltage or electromotive force that you will get out of it. That's what it means. So the faster you spin this, the larger the magnitude of the electromotive force. And then we talked about, it was a storytelling. This was cute. These little things that I'm talking about is going to become crucial next week. Voltage is what drives current. Voltage goes up, the current goes up. The voltage goes down, the current goes down. All right, and this is called a sine wave, so it's this one. And they will be in phase, whatever that means to you. So that's something that we will have to discuss next week. This thing is mathematically, it's going to get kind of cumbersome. It's going to be fun if you're a physicist. If you're not, if you're an engineer, hopefully you'll benefit from it, especially if you're getting into electrical engineering, because you'll be using these concepts forever. All right, so voltage is what drives currents. Voltage does this dance, the current does the same dance, and they are going to overlap. They're going to, their peaks and their valleys coincide, which means that they will be in phase. Voltage is what drives current. On average, you will get 0 voltage and 0 current from the power company. And this is the maximum amount of voltage that you will end up getting from the power company. So instead of paying for the voltage or the current, you end up paying for the power, because on average, you're not getting 0 power. On average, this is the amount of power that you end up getting, because notice that the sine of omega t squared is not going to be 0. Ooh, it's not going to be 0. It's not going to be 0. It's not going to be 0. It's kind of visual. On average, you get 0 voltage because the 0 axis, time axis, right? The time axis right in the middle. Here's your maximum voltage. Here's your minimum voltage, which means that you end up getting 0 voltage on average. When you look at the square of the sine wave, notice that it's above the 0 axis. All right, so on average, you're getting something, and you're getting half the maximum value in essence. All right, so out of that, all of a sudden you come up with a conceptual way of figuring things out. So we pay, power company is fair. They say, hey, you know, just pay us the average of whatever it is that we're paying you. So they charge us for the average power. So that's the maximum amount of current times the maximum amount of voltage that they give us, and they divide by 2. All right, you're paying for the current, you're paying for the voltage, except you're paying half of the product of the current and the voltage in essence. And if you press the issue, they will say, yeah, we know on average, we're not giving you any current. On average, we're not giving you any voltage, but we're still giving you something because obviously you're consuming power, you're a consumer. So they say, we're charging you for the RMS value of the current as well as the voltage. So these are non-zero averages. So RMS means root means square. Obviously you take the maximum current amplitude and you take the maximum voltage amplitude and divide them by square root of 2. That's what you do. All right, so you end up using the RMS values for non-zero averages for things which are going to be expressed in terms of 0 averages. All right, so what is it that we're doing here? All right, so we're doing a fast review. So what's the relationship between the maximum electromotive force and the frequency of the spin? It's direct. All right, so spinning a wire in a constant magnetic field, how does it generate electromotive force? Well, because you're changing the flux. All right, change of flux is what generates the electromotive force. You're changing the area, size of the area exposed to the magnetic field by spinning it. In essence, you're changing the angle. That's what it means. And all that awesome math came out of this assumption. You're changing the angle, and you express the angular displacement in terms of its angular velocity, and then you turn around and then call that the angular frequency or something. All right. Relationship between the maximum electromotive force and the frequency of a spin is going to be direct. All right, so faster you spin this, faster the angle is going to change. Faster the angle changes, the larger the electromotive force is going to be. So we have this direct relationship. So electromotive force is going to depend on the number of turns, obviously, and it's going to depend on, this is the maximum electromotive force. It's going to depend on the number of turns, and it's going to depend on the strength of the magnetic field intercepted by this area. So larger the amount of magnetic field, larger the maximum electromotive force is going to be. The bigger the area, the larger the electromotive force amplitude is going to be. And then also it depends on how fast you spin it. All right. So it's going to depend on the angular frequency. All right. So that's it. Okay. This expression is not on the formula sheet. I know that because every single year I say to myself, I'm just going to go back and put it on. And it's mindless work. So I haven't done it yet. So eventually I'll do it probably shortly before I die. Anyway, so this is how it is. So omega represents the frequency. Frequency is the F is the linear frequency multiplied by 2 pi. It's going to give me the angular frequency. So faster you spin this, larger the electromotive force is going to be. All right, let's get back to NASA. Those clever rascals trying to generate electricity in space by dragging a wire through the Earth's magnetic field at 17,500 miles per hour, and they were able to generate a tremendous amount of electricity. In fact, the wire ended up heating up to an extent that end up getting melted off, broke away. So how's that possible? Once again, this is basic physics. It's straightforward. All right, so you got this conducting rod, metal piece. You drag it across a constant magnetic field. In this case, the magnetic field is pointing into the page. What's going to happen to the charges when you drag them across a magnetic field, just like that? All right, so imagine a positive charge alone right here, and then you drag it across the magnetic field. All right, so this requires an advanced usage of the right-hand rule, number 1. So what do we have? Line up your fingers in the direction of the magnetic field into the page, and your thumb is going to point in the direction of the velocity vector. Your palm is going to be pointing in the opposite direction. So positive charges will experience the magnetic force in the opposite direction. And guess what? Negative charges will experience the force in the downward direction. Even conceptually, you should be able to see that it's going to cause a charge separation inside the conducting rod. So the top is going to be positive charge, the bottom is going to be negatively charged. There's a charge separation, meaning that the electric field is going to be pointing in the downward direction through this distance. Oh, immediately you notice that there's going to be a voltage difference between this region and that region. So in essence, this rod now is acting like a battery. All right, so this is called the motional EMF, because the motion of the conducting rod across the magnetic field is going to generate a voltage difference between the top as well as the bottom of this conducting rod. And it's going to act like a battery. In the sense that if I hook a circuit up to this, and if I place a light bulb here, the light bulb is going to light up. That's what it means, because there's going to be current. There's going to be a continuous current in this, because this literally becomes a battery at that point. And that's precisely what NASA was doing. Now that we just did the poetry portion of physics, which is the conceptual physics. Well, I wonder how this looks like in real life when you express the same idea mathematically. Guess what, guys? It's going to look the same, except it's going to look a little bit more sophisticated. All right, so there's going to be a charge separation. Here's your positive charge. And imagine that this positive charge alone is moving this direction inside a constant magnetic field. Pointing into the page and using your right hand, you will notice that the positive charge is going to get dragged in the upward direction. So every single positive charge is going to get dragged in the upward direction, and every single negative charge is going to get dragged in the downward direction. All right, so conceptually, you should be able to see without even doing the mathematics. There's going to be an automatic charge separation inside any metal. You don't need to be a NASA engineer. Inside any metal, it could be your car. I don't care what it is. If you're moving across a magnetic field with a metal piece in your hand, on your body, there's always going to be a charge separation. All right, so one portion of this conductor is getting positive charge, the other portion is getting negative charge. This happens all the time. You're probably hearing it the first time, but this happens all the time. There's nothing new here. All right, now we're just setting up the map. We will say that the charges will get separated until this magnetic field strength becomes equal to the electrostatic force between these two opposite charge regions. All right, that's a good assumption. All right, so in terms of problem solving, I don't know if you guys are noticing it. I'm just writing some cute little comments here and there, like, hey, you need to explain more, you need to show more work. And most of you guys, this is the second time you're taking it with me, so you kind of know what I'm looking for, and your professors, when you guys move on to universities, will expect the same thing. You will have to show work. And showing work means you have to also explain stuff. Because hopefully you guys are noticing that what drives math is not the math itself, it's your understanding of what's going on in reality. You're just modeling what I just explained conceptually in the form of math. It's the same thing, okay? Physics is not, though it is not mathematically, mathematics is just an expression of what you're thinking about. Here, all of a sudden, all that blah, blah, and all of a sudden I'm going, wait a minute, I can only separate these charges. These charges are going to move in opposite directions until the electric force balances the magnetic force. All right, so the question becomes, something. So the question becomes, what is the amount of electromotive force that we're going to be able to generate once these charges stop moving? So the charges are going to separate until they become static, and they will become static, obviously, when the electrostatic force balances the magnetic force at that point. All right. All right, so I'm doing a visual for you. The magnetic field is pointing into the page. The positive charge is moving in this direction. So it's going to experience the force in the upward direction. So the positive charges will experience the magnetic force in the upward direction. The negative charges will experience the force in the downward direction. So there's going to be a charge separation. All right, so positive region is positive charge, and negative region is negative charge. Notice that the electric field is pointing from a positive charge region towards the negative charge region through a separation distance of L. All right, so combination of the strength of the electric field and the separation distance is going to give us the voltage difference between positive and negative charge regions. In essence. All right, and we want to know what that voltage difference is, so we're looking for an expression, mathematical expression for that one. And that's how it is done. Okay, that was cute. We just jumped around a couple of times and we didn't go anywhere. All right, so I want to get to the very end first. Stop it, let's sit down, let's do it. We will backtrack it from there. All right, so this is the final expression that we come up with. Let me just talk about the final expression first, and then we'll just backtrack real fast and get it done within the next minute or so. All right, so this expression gives you the electromotive force with a voltage difference between two opposite charge regions created inside a conductor. All right, and those regions will become created when the charges become static. That's what it means. All right, so which means charges will become separated until the electrostatic force, the attraction between two opposite charge regions, balances the magnetic force. All right, so according to this, the electromotive force is going to depend on the speed of the conductor. So faster you move it, the larger the electromotive force is going to be. It's going to depend on the length of the conductor. All right, so if you have a cell phone, obviously, I don't care that you're driving at 17,500 miles per hour. It's not going to make that much of a difference. But if you have a wire which is about 13 miles long, obviously, it generates a large enough electromotive force. It depends on the strength of the magnetic field. So in this case, NASA was using the Earth's magnetic field, which happens to be fairly weak. And also depends on the sign of the angle of theta. So the question is, okay, everything makes sense, but where's this angle coming from and why is that important? Okay, so that's the reason why we need to just go back up to the previous statement. Evidently, what's important is your velocity. All right, so what determines the strength or the value of the maximum electromotive force, value of the electromotive force, is the perpendicular component of your velocity relative to the strength of the magnetic field, relative to the direction of the magnetic field. Forget the strength of the magnetic field, relative to the direction of the magnetic field. All right, so it has to be the perpendicular component of the velocity relative to the magnetic field that becomes important in essence. All right, so if that's the case. So obviously the strength of the electric field and the magnetic field is not the same. To create a static case, so this becomes, it starts to act more like a battery in that case. And then so electric field strength equals the magnetic field strength. And I noticed that this is the velocity relative to the magnetic field. This is a dot product expression in the scalar form. All right, so this becomes the vertical component of the velocity vector. All right, so the rest of it is straightforward. Here's the electric field component, here's the magnetic field component. They're going to be equal to each other. So you come up with the electric field component expressed in terms of the magnetic field component. And the magnetic field component is multiplied by the vertical component of the velocity vector. All right, so electric field component multiplied by the separation distance, which means that you're going to multiply both sides by the separation distance, is going to give you this formula at the end. All right, so that's exactly what NASA was doing. Metal.
If you put a wire inside of that tether, you now have a moving wire that moves across a magnetic field. That magnetic field in this case is Earth's magnetic field, and the motion is the motion of the space shuttle moving at very fast, high velocities, orbital speeds.
Flying down here, Jeff.
The moving wire in the Earth's magnetic field generated 3,500 volts, enough energy to power a space station.
Okay, we see the tension go way down, but the tether's still going out fine. Very slight lateral oscillation.
The tether was clearly visible from the ground. It was one of the biggest man-made objects ever sent into space. For 5 hours, the tether swept through our planet's magnetic field, generating more and more electricity.
At the boom. The tether has broken and is going away from us. Get it on the TV court. Please get it on the TV. The tether has broken.
Copy.
Going to photograph, it's floating away from us.
The wire was generating so much electricity that a spark jumped from the wire to the satellite deployment system and burned through the tether. NASA will try the experiment again because it could lead to a new, more reliable power system for space stations and help avoid situations like the Mir mishap.
What we're moving to actually is if we drive current in the opposite direction in the tether and we can force the current to go the other way, it becomes a propulsive device. So a propellantless spacecraft, the next generation of space travelers may be using electric propulsion devices as opposed to chemical propulsion devices. A little Star Trek, if you will.
All right, so you got the conducting rail. All right, so you got a conductor just like that. You're moving across the magnetic field at right angles to it. Faster you move this, larger the electromotive force is, so it starts to act like a battery. That's what it means. And then if you hook a circuit to it, there's going to be current inside the circuit. in essence. All right, so what am I looking for in this one? Okay, we already had a discussion regarding. All right, that's good. All right, one more remark before we move on to the next section. All right, so what happens inside the wire when you change the flux within the loop? All right, so you're changing the magnetic flux inside the loop. Inside the wire, you got current. What's driving the current? All right, what's driving the current is the voltage or potential, obviously. So the big question becomes, how does the voltage or potential drive the current? Guys, there's a reason why I end up spending like almost two weeks talking about this now. What drives the current is the electrostatic force field, guys. When we're talking about voltage difference, to engineers, it's voltage difference because you guys just think that this is kind of like poetry or something. The words don't mean anything, much of anything to most of you guys in general. And I'm trying to change that. To a physicist, the voltage difference means that there's an electric, there's number one, there's a region that contains two opposite charge regions. And there's going to be an electric field pointing from the positive charge region towards the negative charge region. If charges are moving in the same direction, just get it into your heads, guys. They're moving because they're experiencing a force. That's what it means. Voltage difference means there's a force field within. And charges are being forced to move in the same direction, which means that there's a force acting on these charges. So what that means is, if I'm varying the strength of the magnetic field within a region, just like this, notice that there's no wire here. I'm automatically creating a circulating electric field. That's what it means. You don't need to have a wire there. All of a sudden, it becomes a little bit more abstract. I'm putting you right now in the mind of Faraday. This guy figured things out, and he's just thinking, wait a minute, what's driving the current? They call it the electromotive force there. So what is that electromotive force? Electromotive force, in essence, is the electric field. So when you vary the strength of the magnetic field within a region, I don't care what region it is. If you vary the strength of the magnetic field within that region, you're going to end up causing a circulating electric field. That's it. This becomes the Faraday's law. I took the wire out of it. At this point, it's no longer engineering. This is pure physics. It's called theoretical physics. This is what's taking place in the imagination of Faraday. This guy is looking at it in his mind. He goes, oh, if I vary the strength of the magnetic field within a certain region, it's going to cause a circulating electric field. He's not thinking electric field, of course. He knows that there's some kind of a force field involved, and they call it the electromotive force. That's a circulating electric field. That's what we call it today. So changing flux will induce a circulating electric field within that region. Now, this is going to become important because things will get somewhat theoretical for you guys. So here's what we're looking at. Oh, it's changing magnetic flux in a certain region. That's going to induce an electromotive force, and the electromotive force is what drives current, which means that the charges are moving in the same direction. The reason why the charges are moving in the same direction is because they're being forced to move in the same direction, meaning that there's a force acting on it. So which means that even if you don't have charges within that region, even if there's no wire within that region, if you were to vary the strength of the magnetic field within any region, you will end up getting a circulating electric field within that region. So now that I told you the story, let's look at it again from a mathematical modeling perspective. There's there, I'm varying the strength of the magnetic field within that area. I'm doing the Faraday's law. By varying the strength of the magnetic field, I'm just changing the flux, so it's generating an electromotive force. And we know that electric field times the separation distance between two opposite charge regions is going to give the voltage difference, and we know that voltage is what drives current in essence. All right, so we had this analogy. Literally, I spent 2 weeks blabbing about it. All right, so the voltage simply means, hey, we got two opposite charge regions, and obviously there's a strong electric field or some sort of electric field from positive and negative charge regions. And then if I were to place charge in it, you know what? They will get pushed in this direction. Thus, we will have current. That's what it means. So what that means is change of flux induces an electromotive force. In turn, the charge move in the same direction, right? Which means that it must be causing a circulating electric field. So the change in flux causes a circulating electric field. That's it. Take the wire out. We don't even need it at this point. It was a scaffolding. We don't need the wire. No longer now it turns into pure physics. That's the beauty of it. We don't need a wire. So there's going to be a circulating electric field, and if you place a charge there, obviously the charge will experience a force. It will accelerate. All right, all of a sudden we came up with an interesting thing. So we end up getting a circulating electric field, and this is the meaning of this expression. So the electric field is going to be along the direction of the curve. So change of flux causes an electromotive force, or change in flux is going to cause a circulating electric field. This expression is the same as this expression. This is the new expression. So the electromotive force means the voltage is the same as current times the separating distance between the opposite charge regions. Guess what, guys? There are no two opposite charge regions within the wire. What's happening is just change of flux is going to cause a circulating electric field. Okay, you don't even need this expression of the electromotive force under the circumstances. All right, so you don't need, because it was tough to explain, like, how, are you generating, I don't know, electro-opposite charge regions inside the wire? No, you don't need to. It just introduces, because you try to visualize this within this context, you don't need to. I'm just changing the flux within that region. It just causes a circulating electric field. And you can call it the electromotive force. You don't need to even call it voltage at that point, because it kind of mathematically resembles the concept, but in reality, it's an unneeded concept. All right, so any variation of this flux is going to cause a circulating electric field within that region. That's it, which we will refer to as the electromotive force. That was cute. All right, so, okay, let me just check to see if I have a solution for this. Okay, I do. Cute. Okay, I was hoping that I had the solution for it. All right, this is problem number 6 from the handout. All right, evidently I have to go back to detail after the lecture sometime today and pull out the right handouts for you guys. This stuff there is the college physics stuff. We'll still need it. All right, from now on, starting with the previous chapter, okay, the Faraday law, starting with this chapter, this is the Faraday law. All right, your test will be in the multiple choice format. Okay, so you'll have 10 problems, multiple choice problems. Problems are going to be straightforward. Just know how to use the formulas. You will have 5 minutes per problem. They're not complicated problems. Just want to, at this point, I'm more interested in, do you know the concepts? Can you find the right formulas? All right, so that's the way the tests are going to be. The previous ones I needed to see work because you will have to build upon that sort of math in the future. This stuff is just understand the concepts well enough to actually find the right formula. All right, so let's take a look at this problem. This is a straightforward problem in terms of, all right, so what do we have? They give you the radius of the flux region. So I think the flux region is capital R has to be the flux region because I'm looking at the amount of magnetic field intercepted by that area. So that would be your flux region. Now what's happening is we're varying the strength of the magnetic field within that region. All right, so what is the magnitude of the induced electric field? All right, so here's your yellow stuff is your flux region. So we are interested in the magnitude. What's the magnitude of the electric field within this small radius that you're looking at? So the flux region is going to be 8.5 centimeters. And then we're interested in this strength of the circulating electric field at a radial distance, which is going to be 5.2 centimeters. And then the next question is, what would be this magnitude of the electric field outside of this region, which is about 12.5 centimeters? It seems complicated. It's not. Okay, that was good. All right, now let's take a look at the map. All right, so this is, all right. So the first thing we will do is let's take a look at the strength of the electric field within that region, lowercase r. All right, so when you vary the flux caused on circulating electric field, you're varying the flux within the entire region. So what this means is, if you're looking at this, we are going to be interested in the variation of the magnetic field only within the area of this lowercase r that you're looking at. All right, what causes the circulating electric field is the change in flux within the region inside this region where the electric field is circulating. All right, so which means that this A that you're looking at is going to be the area within. So it's going to be pi r squared in essence. So that's what we're going to be looking at. And then this ds that you're looking at, this is going to be, you're looking at the curvature. ds represents the total circular path that you're looking at. So it's going to be circumference, which is going to be 2 pi r, the expression that you're looking at here. All right, so let me just take a look at the expression and check to see what's going on here. All right, so what I'm doing is I'm moving this expression to the left. We're looking at the strength of the electric field at a distance of lowercase r, which is this, smaller than the radius of the region within which you're looking at the flux. All right. All right, and the change in flux is going to be expressed in terms of changing the magnetic field, strength of the magnetic field within the area of this lowercase r, or within the area which is related to the lowercase r. All right, so this ds is going to represent the circumference of that area. And the area that you're looking at is obviously the area within, so it's going to be pi r squared. All right, so we are right here at that point. So let's just get down to that expression. All right, so what do we have? So on the left-hand side, you have E, and then you got the integral of ds. line integral of ds, which happens to be 2 pi r. All right, so ds becomes 2 pi r, e is the same e. Here's the area of that region, so it's going to be pi r squared. All right, so the negative sign is going to be coming from the Lenz's law. Here's the change in the strength of the magnetic field. All right, let's do that. All right, so let's go, okay. All right, so after the cancellations, this is the expression that you end up getting. So what that means, the statement says, within the region where you have the flux, strength of the electric field is going to increase, strength of the circulating electric field is going to increase radially away from the center. That's what it means. All right, so that's, you know. But what happens to the strength of the circulating electric field if you're outside of the region of change of flux? All right, now you're outside of the region of change of flux. All right, in this case, your lowercase r is going to be larger than capital R. Capital R is the region of the change of flux. All right, so obviously only within the region of change of flux. Yeah, I gotta find a way to explain this better. Okay. She needs to get back. Okay, let's just get back to it. I was looking for a visual for this one. I don't see a visual. Let me check to see if there's a visual. Okay, yeah, there's a visual. Let's get back to the visual. Okay, it's easier to explain if there's a visual. All right, guys, the green stuff that you're looking at. Okay, so I'm changing the flux within that green region. All right, notice that this is the radius of the green region, which is capital R. All right, so the change of flux within this green region that you're looking at is going to be responsible for the circulating electric field outside. All right, so it's going to be blah, blah, blah. I should have done an animation on this, but that's fine. I'll do it in the future. All right, so, okay, I'm going to just focus on this formula because this formula gets reduced into this one, in essence. All right, so the electric field is outside within this region. Okay, this lowercase r is going to locate the electric field for you, the circulating electric field. So this ds in essence is going to be still 2 pi capital R. All right, so this is the outside region. But the flux is changing only within this green region. So the area here is going to be pi capital R squared in essence. Okay, so that's what it means. So circulating electric field is going to be at a radial distance, which is going to be larger than capital R. And the flux is going to be changing within this region, which is going to be pi R squared. And when you do the mathematics, this is the expression that you end up getting. So the strength of the electric field outside is going to depend on obviously how fast you vary the magnetic field within that region inside. But once you're outside of that region, though, notice the strength of the electric field is going to diminish inversely with the radial distance.